Hi there, welcome back to the Formulaic Approach channel. I'm sorry that I've not been releasing content for a while now. I've been everything. I've just been very busy. But I'm releasing this because a student demanded that I prove why A is equal to V squared over R, where it comes from, okay? And I promise you that if you don't even know circular motion much, you should be able to follow me, okay? But of course, you should watch my video on vectors too to be able to understand some of the things that I will talk about here in depth. I promise you should get it. So now listen, one of the things that I'll first show you is the formula that you probably already know, which is that V is equal to R omega. That is linear speed is equal to R radius of the circular path times the angular speed. All right. After proving this, I will now show at the end of this video. I'll also prove some of these formulas. Okay. Now, since you already know this, I'll prove this too. I'll also show you how this came about. Now, the first thing we want to do is we want to let's consider the motion of a body that is moving in a circular path. So this is a circular path here. So the body moves, let's say, so this is the center. You know that the acceleration of the body is always directed towards the center, right? So the body is accelerating in this direction towards the center. But of course, the position vector points away, isn't it? All right. But then again, the body has centripetal. The body has velocity that is tangential, so we call it tangential velocity. Tangential velocity. So the tangential velocity is always perpendicular at every point to the centripetal acceleration. This is called the centripetal acceleration A, and it is a vector that points into the center of the circle. Why? Because the centripetal force is the force that keeps this body in this circular path attracted to the center. Is that clear? It pulls it towards the center. Then this velocity is always tangential. Okay, the magnitude of velocity at every point on this curve is tangential to the centripetal acceleration. I hope you are following. Okay, now of course you should already know in fact that why do we call it velocity? Because the student also asked me that since we call it speed, since the body has constant speed, why are we calling it velocity? Now in numerical value, the speed around these objects, that numerical value is the speed. The speed is the same throughout. So why then do we call it velocity? The reason why I call it velocity is that you will see that at this point, velocity is pointing in this direction. At this point, velocity is pointing in a direction that is always tangential to the point we pick it from. Is that clear? So because the direction of velocity is always changing, that is why we call it what? Velocity. The direction of velocity is always tangential. So to the point, to a particular point. So it is changing at every point. If I snap cut the rope that is maybe we are using to swirl that thing around. If I cut it, what will happen is that this body will move in a direction that is tangential, right? The body that is in question that is moving. Is it clear? So this is the reason why we call it velocity and not speed. It has a constant speed in numerical value, but we call it velocity because the velocity is changing because the direction of that velocity is always changing. Is it clear? All right, so as I said, acceleration directed towards center, velocity is perpendicular at all points. Now, the first thing we want to do in order to prove this is that we will, let's parameterize the position vector, okay? So the process of proving is, okay, the first thing is to parameterize. How do you even spell parameterize? Position vector. Now, what is our position vector? Now, remember position vector here. Let's call it R. Our position vector R. Now, with respect to time, okay? Now, because of course this body is changing its position with respect to time. So let's say at a particular point in time it came and got here. Now, let's draw our Cartesian, our coordinate system, our planes, Now, by the time this body got here, you agree with me that, let me clean this now, just watch me, it's very simple. By the time this body got here, okay, you'd agree with me that it has a particular maximum horizontal displacement. Let's call that x sub I. X, that is in x-axis, I to show is also pointing in that direction. In vector, we use I for x-axis. Then you also believe with me that it has a particular vertical displacement from this point. So we parameterize it using xi and yj, okay, with the rope that is keeping it in place at a steady radius, at a particular radius, the radius of this circle. So you saw the way I parameterize it. So at this point in time, this body is at this point in the x-axis and has this displacement, vertical displacement, has this horizontal displacement and vertical displacement. If I use this point here too, it's the same. It has this vertical displacement and this horizontal displacement. If I move the body here, for example, if I move it here, it will have what? It's the same thing we are going to do. We'll parameterize it this way, that we have a particular y displacement, horizontal displacement, and vertical displacement. Is it clear? With the radius staying the same because the circle is perfect. Exactly, the circular part is perfect. Now follow me. So how do you parameterize? Let me bring it here. So the position vector, therefore, r in terms of t, the position vector r is going to be defined by since they are vectors, we are going to do vector addition, right? So how do we do the vector addition? That's just xi plus yj. Exactly. Plus yj. Now, what is xi here? Now, the first thing we want to do is this. You know that this position here, there is going to be is at an angle theta, right? It has covered an angle theta from this position. It has covered an angle theta. Here too, it will have covered an angle theta, depending on where I'm looking at it from. So I want to look at it from this vertical horizontal line. So it has covered an angle theta. So if that is the case, then I can tell you from here that what will be the value of sine theta? Sine theta is going to be the opposite, which is y sub j over adjacent, over hypotenuse, that is r. Is it clear? So if that be the case, then y sub j becomes r sine theta. Is it clear? All right. So since it's being defined in terms of j, I can still put my j here. Since it's a vector, I am not doing the vector addition now. I'm not doing the addition itself, where I will have to square this guy, take the square root. You remember that thing, right? Good. So then for x of j, that will be cos theta, I think. Cos theta should be adjacent here, x sub I over hypotenuse r again, okay? So x sub I becomes r cos theta. But of course, I can write this as r cos theta I, okay? Yj will also be r sin theta j. So I can write my position vector. Remember that is my position vector. Position vector r in terms of t. So look at the way I parameterized it. I just created the position at a particular time. Is that clear? This position at a particular time has both x and y values. Is it clear? This position has both x and y displacements. All right. So we have t equal to, what is xi? X sub I. R cos theta I. Then plus yj is r sine theta j. Okay, so we are getting somewhere now. It's making sense now, right? So r in terms of t is going to be written as, now how can we write theta in terms of t? So that's such that it contains this t. The position at a particular time, that's what we mean by this, okay? The displacement, the position at a particular time, the position. You know, position is also a vector, right? So we have r cos theta becomes, recall that the angular speed is equal to d theta dt, okay? Or basically use the values theta over t, that is angular distance covered per time. Omega is equal to what? Angular distance, that is, remember that this one is angular velocity. Omega is what? Angular velocity. So the angular velocity is going to be what? Angular displacement over time. Is that clear? All right. So it means therefore that from here that omega, that theta can be written as omega t. Okay. So theta is omega t from this equation. Theta is omega t by the time you cross multiply. So omega t. What I tried to do then, you might be asking why am I changing it? I'm trying to write it in terms of t. Is it clear? Then plus a, which is r sine omega t again, j. Then you now ask me, Master, why did I have to start from position vector? Because remember, if you differentiate position vector, you get velocity. If you differentiate velocity, what do you get? Acceleration. So that's why I want to start from there in order to get acceleration. Is that clear? Good. Now, so now from here, we can therefore now begin our work. We can differentiate now. Let's differentiate. So by the time we differentiate this, we'll get what? If you differentiate position vector or displacement vector, what will you get? You will get velocity, right? So velocity at a particular time is going to be dr dt. Exactly, I don't need to write dt there again. Dr dt. So let's differentiate this guy. So differentiate this, you get r times, differentiate the inner function, d omega t is going to give you omega dot cos, differentiate cos omega t. Derivative of cos is minus sine, so you have minus sine omega t. Is it clear? So plus, differentiate this, you have r again, differentiate the inner function dot omega again. Is it clear? Put your I back. Exactly. Then differentiate sine of this gives you cos omega t, cos of that same thing. Everything j rather. Everything I. So we write our v, velocity vector in terms of t, is the derivative which gave us r times omega. That's okay, there's negative here. That'll be minus r omega sine omega t I plus r omega cos omega t j. Is it making sense to you now? So this is the velocity vector. So if I wanted to write the absolute value of the velocity vector is actually r omega. Do you see now it proves it, right? And you now tell me, Master, how did you get that? It's very simple. If you look at this thing very well, but it's negative though, it will be negative. It's negative. And I'll tell you what the meaning of what the negative there means. But what I want you to watch is this. So see, if I wanted to do this, I want you to see something. See, I will write this. Before I write this, I'm going to clean this and show you why that's absolute value there that I wrote is just r omega. You say, Master, how did the sine and cos disappear? So simply look at this. Look at this. If I collect r, if I bring r, no, omega, let me bring omega out. Since omega will have the same value, so omega comes out because you know that it's linear speed that is changing. Angular speed does not change. Angular speed is similar for all the particles in that circle or the substance everywhere in that circle. Is it clear? Angular speed does not change. That's one thing you should know. Okay, so omega is the same, into brackets. Omega is common between both of them then, right? So let's eyeball this negative first. How do we do that? So let's put the minus here. Okay, let's rearrange this. I want you to see how V equal to R omega. That's not what I'm proving though. I just want you to see it. See. Let's rearrange this. Becomes R omega cos omega t J minus R omega sine omega t sub I. So in this case, at both I and J, omega is going to be the same. So if we collect omega out, then we have equal to omega into bracket rather R cos omega t. Now, if I put plus here, and let me put plus here, I have to put minus here so that to change it back to minus. Is it clear? Good. So V in terms of t becomes this. Then we have factored out R omega, so we have R sine omega t I. Now, if you look at this G, if you look at this very well, see. If you look at this very well, R cos omega t J, R cos omega t, R sine omega t I, and R cos omega t J. I think I've messed it up. Okay, I rearranged, yes. Okay, the point I want to show you is that, see, this value, this whole thing, and gives you back your R, gives you back R. R cos omega t J plus R sine omega t I. Even though I is interchanged here, but basically it's still R. So the entire thing here is R. So omega times R. Is it clear? But you might not really agree now because you're feeling like, well, here it is cos that carries I and J. Anyways, if that's your argument, then leave it. But you already know where this is coming from, right? All right. I'll prove it in another way. I'll prove that in another way. But if you understand the maths here, it's basically the absolute value is going to be omega times R. The negative only shows you that it's going in the opposite direction to the position vector. Is that clear? All right. But anyways, let's continue. So how do we get acceleration? Acceleration is going to be dv dt. Is that clear? So we have to differentiate one more time, right? So what I will do is I like to pick it back from here. So I'll clean all of this. So now, if I start it from here again, then I have that acceleration, which is dv dt, will give us negative of, differentiate this function, gives you the same thing in terms of t. Now differentiate this inner function first. Derivative of omega t will give you omega. Then derivative of sine omega t will give you cos omega t. Everything I. Okay? Then plus derivative of this is CR omega. Derivative of cos of this is minus sine. First differentiate this to give you another omega. Then times minus sine omega t all j. Is this clear? So by the time you write this, a becomes minus r omega times omega, r omega squared cos omega t I minus plus r omega squared sine omega t j. Okay, now so here comes the rule I told you before. So a therefore becomes, since omega is the same, omega never changes, angular velocity never changes. So omega becomes, omega squared can be factored out. Let's put our minus here still, okay? Or now we can even rearrange, it doesn't change anything now. It doesn't change anything now. Watch, let me rearrange so that I have positive first. So A becomes r omega squared sine omega t j minus r omega squared cos omega t I. So if this be the case, then omega is common. So A becomes, let me come and put it here. A becomes omega squared is common between r sine omega t all j minus, if you remove omega squared, the r cos omega t I. Now if you look at this, this is perfectly what we had in the beginning. r sine omega tj, look at it here, then, but it is plus here, watch, it is plus r cos omega t I. Okay, so how do we change this? We'll come and put the minus outside, so it becomes minus, A becomes minus omega squared r sine omega tj plus r cos omega t I. So this now looks exactly like what we had in the beginning, right? Which is this. So this entire expression here has been repeated here. Makes sense? So I can therefore say that acceleration is equal to minus omega squared times r vector, the position vector r. So it means that A equal to r omega squared. Now if I want to take only the numerical value, I can eyeball this minus. Minus just means that acceleration is in one direction, position vector is in the outward direction, the opposite direction, everywhere. It is even here. Acceleration is pointed always towards the center because it's centripetal, and the position vector will point outward. That's the meaning of negative here. Is it clear? All right. So if that be the case, recall that we said that V is equal to R omega. I tried to prove that here using this, but some people may not get it. So I'm going to show you again, but since you already know where this formula is coming from, for those of you that have seen, that understand circular motion, I'll still prove it, just watch. Then it means that omega here is going to be V over R. If that be the case, what we got was A equal to minus, let's remove the minus now, so it's R omega squared, and omega is V over R. So we say A equal to R times V over R all squared. So A becomes R times V squared over R squared. This takes care of one of the R's. So A becomes V squared over R. Is it clear? So I hope I've been able to prove to you how centripetal acceleration is equal to V squared over R. All right, now let me try and prove to you why V, velocity vector itself, the linear velocity. Okay, this is what we'll do. Let's now talk about relationship between linear and centripetal, and linear acceleration and angular acceleration, and also linear velocity and angular velocity. So this is the equation that relates them. How do we prove this equation? The relationship between what? Linear and angular velocity. Linear velocity is V, angular velocity is omega. Let's prove this. Let's prove this if this is correct. Now remember that the angular speed is going to be changing. See, look at our circle here. The speed of a particle that moves from here to here is going to be, from here to here, is going to be the angle covered, the angle theta covered per time that it chooses to cover that. Does this make sense? Good. So if we want to take it by derivative, then I can therefore say that omega is equal to what? D theta dt. You all agree on this, right? Good. Recall also that velocity is displacement s over time, right? Well, you know that one, right? That one is common. Linear velocity is this. So that is ds dt. Good. Now also remember in mathematics that s, our distance s, is going to be theta times r. That this is the displacement is going to be the angle, or think of it this way, that the angular displacement covered. See, look at our circle now. The angular displacement from here to here, for example, is going to be the how do we put that now? You should know this equation now, that theta over 360 times 2 pi r, length of an arc. Is that okay? Length of an arc, S is theta r. You know that in maths, right? So that is where I got this from. So this linear displacement, and here is, that is theta times r, okay? Then you can now begin to ask, how did we come about that and all of that, and that we are supposed to have sine of theta, and we usually say, because we measure in radians, okay? In radians. If I have what? If I move from here to here, a very tiny distance theta, a very tiny angle theta. You know, I covered R here. So this place, this place is S. Is it clear? By the time I relate them, this opposite and this hypotenuse, any side of here is hypotenuse. Hypotenuse, both the hypotenuse and this place, they are the same, because the angle I covered is very small. So what? I want to use SOHCAHTOA now. So sine theta we got to what? Opposite, which is S over hypotenuse R. Then you now tell me S should be R sine theta. Now then I'll tell you that if angle is measured in radians, a very small angle will be the same as theta. So that's where this formula comes from. Is it clear? All right. So for very small angles, since angle is to be measured in radians, this guy will be the same like this. So you already understand this. Now from here, I can begin to now manipulate things. Now you know that omega is d theta over dt. Now, I don't even know where to go to now. You remember, this is ds dt, okay? Now how we're going to get here is very simple. What you will do is this. You know that theta is also omega t, right? So S can become omega t times R. Okay? Omega t times R. No, this doesn't give us anything yet. Okay. Let's go from here. Let's go from here directly. You know V is ds dt. Then V can therefore be d theta R dt. Is that clear? D theta R dt. So since we are measuring, we are differentiating displacement with respect to t, not the radius. So what will happen? V becomes R times d theta dt. Okay, we are getting somewhere now. So look at this, d theta dt, omega. So V equals to R omega. So you see, everything is provable. That's the truth. It's provable. So that's where we prove it. Now let me now show you another relationship between angular acceleration and linear acceleration. Now what is linear acceleration? Linear acceleration is denoted by A. And angular acceleration. So we have relationship now. Relationship between, I hope this my marker is working well, because one of the reasons why I've not been shooting is also because of marker. I've not been able to buy ink. Like I've not gone out to buy ink. So I don't have enough markers. Relation between angular acceleration and linear acceleration. And that should tell you how busy I am. I couldn't even go out to buy ink. Okay, so now what is angular acceleration? This one is denoted by alpha. Linear is denoted by A. Is it clear? What's the relationship between them? You must have seen it before, that A equals to what? Alpha R. Just the same way. Just like as we said, S is going to be displacement, linear displacement to be angular displacement times R. Linear velocity will be equal to what? Angular velocity times R, omega times R. The same way, angular acceleration of what? And linear acceleration of what? Angular acceleration times r. But let me quickly prove that to you. So since from here we know that angular acceleration is going to be angular d omega, like change in angular speed over change in time, right? So mathematically we say angular acceleration is what? D omega dt. That makes sense, right? So by the time we have something like this, v equal to r omega. Now let's differentiate this. If we differentiate this, it will become v equals r. Now that is d omega r dt. You understand, right? Because that's acceleration. dv dt is the same as d omega r, and that is dv dt is linear acceleration, right? Good. So linear acceleration, a therefore becomes d. Now r is not affected because acceleration is respect to velocity, right? R is unaffected, just like we did here. So it becomes r times d omega dt. What is d omega dt? Alpha. So A equal to what? R alpha. So that's how to prove the relationship between them. All right. If you want me to shoot a long content on circular motion, put down in the comment section and I will do it immediately. That is if you don't know linear acceleration and circular motion. I plan to shoot one video, a long content on velocity, linear motion, translational motion. But because I've not seen comments mentioning it, that's why I've not shot it. So let me know if I should shoot it. I'm going to shoot a long content and I'll solve questions. In that one, in the video I'll shoot next, I may not prove this, and I might prove some, but I will definitely solve a lot of questions. God bless you as you subscribe if you have not already.